So chapter 13 is now going to expand on everything that we've been doing so far with hypothesis testing. So remember, what we think about what we've done so far with hypothesis testing is we looked at one sample means, try to figure out is one sample, is that going to be different than, say, a population? Then we started moving on to two samples. So then the natural question is, what do I do if I have more than two samples? So this is what's going to be called, we're going to be using what's called the one-way ANOVA test. ANOVA, this is an abbreviation for analysis of variance. So variance, we said that's the square of standard deviation. It tells us some type of spread of our data. Okay, so what we'd like to determine is there a significant difference between several group means? And what I mean by this is I mean more than two. So if I have three or more groups, we're going to have a brand new test that is going to be the ANOVA test. So a few assumptions. As I had mentioned a little while ago, there's always assumptions behind the scenes. But the more technical, the more difficult some of these tests become, or the more that they're able to do, there's more assumptions that kind of restrict the ability to do them. So there's a few assumptions that we should realize is one, each group is assumed to be normally distributed. If you don't have every group is approximately normally distributed, you can't use the ANOVA test. So that's something that taking more advanced statistics, you'll figure out what could you do instead. It gets a lot uglier, but in general, hopefully your data, each group is going to be normally distributed. Next assumption here, all samples are random and independent. So we don't have overlapping people within each group. Each group is going to be independent of each other. No one's going to correspond to more than one group. And the last important assumption is that the populations are assumed to have equal standard deviations. This is, again, very similar to the first one. It's a little bit tricky. Now, there's not really formal testing that you do. This is one where you visualize your data. So because we're looking at multiple groups, in practice, what you would look at is you would try to create box plots for each of your data. So you'd look at this one, and then maybe you'd pick this one over here. And then you would take a look at this one over here. And so you would plot all three or however many of these groups you're looking at. You would visualize and say, approximately, do they have the same standard deviation? If they do, great, you're in good shape. Roughly the same type of spread. However, if you were to try to do this test where then your standard deviation, if you have these three groups, your test is going to become very flawed. If the standard deviation is vastly different, this test is no longer going to work for you. So just a few little assumptions for you to be aware of, that this isn't just a magical thing you can always apply. So for ANOVA, so if we're trying to come up with a hypothesis testing for ANOVA, we have our null hypothesis is going to be that every single one of these means is equal to each other. So the mean of the first group is equal to the mean of the second group, which is equal to the mean of the third group, however many groups there are. So if there are five, there'd be five of these equal to each other. But then the alternative hypothesis, this is now a little bit different. The actual symbolic notation for this gets a little bit trickier, so you could try to use that. But in general, it might be easier to just say this phrase. At least one mean is different from the others. We're not trying to say that all of the means are different. We're not trying to claim anything about all of them. We're just saying that one of them is not like the others. Right, so one of these things is not like the others, right? So it's not the same, but we don't know which one. That's one of the unfortunate restrictions that we have, is that we can't figure out which one is the oddball out. You could do more advanced testing on your study to figure out which one is the odd one out, but this just says one of them is different. So the type of distribution that is formed here, we know, so far we've seen normal distribution. This is not a normal distribution. And we've seen student t distributions. This is not a student t distribution. So this type of distribution looks like none of these. This is called an F distribution. So the F distribution is what's going to be formed when we're looking at this ANOVA test. Now, there's a whole bunch of math that goes on behind the scenes, and since you're all at a distance, and I know you're probably just going to turn off the video anyways if I start going on to these long tangents that they're not going to be testable. So long story short, basically what's being formed here is that we're going to be comparing two types of variances, two types of way to describe how your data is spread out. So you're going to be looking at something called the between and then the within. So just real quick, that's just a summary of it, is that you're really trying to look at comparing two variances as a fraction, and then that's why you form this brand new distribution called an F distribution.